So we've looked at the theory behind the Moivres theorem. What we're going to do in this video, I'm going to give you a couple of examples to have a crack at. What I want you to do is read the questions, pause the video, have a crack at the examples, and then come back and check your working against the working I'm going to show you. So here you go. So I've got 3 questions there for you to calculate, all of them using the Moivres theorem, getting slightly more complex. The numbers in the last one especially can be quite interesting. So pause the video now and have a ping at those. So the first one, calculate this number to the power of 5. So 2 bracket cos pi over 5 plus I sine pi over 5. So for this one, you've got to remember that that is your z equals r bracket cos theta plus I sine theta. Alright, you've got to remember that. We're not asking you to write it in this question. It's written for you. You just have to do the step. So essentially it wants z to the power of 5. So it wants 2 to the power of 5 bracket cos of 5 pi over 5 plus I sine 5 pi over 5. We then do each part on its own. So 2 to the power of 5, that's 32. So we get 32 bracket cos pi plus I sine pi. And this is where you check your theta. Now in this case theta is pi, but remember the limits are negative pi is theta up to and including pi. So it's including the pi. It doesn't include the negative pi, remember, but it includes the pi. So this here is fine. We can fire this in the calculator, do it off the top of our heads, whichever you fancy, and get the answer from that. Sine 90 is 0, cos 90, cos of pi is negative 1, so that ends up essentially giving you negative 32. So there you go. Second question, I want you to calculate negative root 3 plus I to the power of 3 using the Moivres theorem. Now this one, we have to write it in polar form first. Then we do our z to the power of 3. So first one I want is r. Now we know that r is equal to the square root of this squared plus the coefficient of the I squared. So it's the square root of negative root 3 squared plus 1 squared. Well, negative root 3 squared is 3, 1 squared is 1, so it's the square root of 3 plus 1, square root of 4, it's 2. We then want theta is equal to tan minus 1 of y over x. Now remember, y is associated with the imaginary part of the number, x is associated with the real part, so in this case, it's tan minus 1 of negative 1 over root 3. So tan minus 1 of negative 1 over root 3, what that ends up giving me is negative pi by 6. So there's my theta. I can then substitute it in. So I know that z is equal to 2 bracket cos of negative pi over 6 plus I sine negative pi over 6. Now at this stage you'd maybe be tempted to turn this into minus I sine of then pi over 6 to get rid of the negative. Keep it in there just now until you've done the z to the power, then have a look, because it may change it ever so slightly and you might have to adjust the limits from that. So in this case, what I now want to do is z cubed, so that's equal to 2 cubed bracket cos of negative 3 times pi by 6 plus I sine of negative 3 times pi over 6. So 2 cubed, well that's 8, negative 3 times pi by 6, well that ends up giving me negative 3 pi over 6, so negative pi over 2, but remember this is now where we can change it with the negatives. So the negative here will disappear, so that will end up giving me cos of pi over 2. Then this one here, because it will then be negative pi over 2 here, I can take it out and it can become minus I sine pi by 2. Then I just calculate each of the parts and see what I end up getting. Cos of pi by 2, cos of 90 is 0. Sine of pi by 2, that's 1. So it's going to be 8 times negative 1i. So I'm going to get negative 8i for this one. So there's the answer for that one. So the final one was I had to simplify 1 plus I to the power of 6 over 1 minus I times the root of 3 to the power of 4. So I had to work these through, simplify them, and then see what I got. Now, we'd be tempted to use the complex conjugate to get rid of the imaginary number on the bottom, as we talked about in previous videos. However, the power stops us from doing that. So what we have to do, use the Moivres theorem to get rid of the powers on the top and the bottom. Then I can look at simplifying it and getting rid of the imaginary part on the bottom and the denominator. So we'll start with the top, the 1 plus I to the power of 6. So 1 plus I to the power of 6. First I have to write it in polar form. So I get my r and my theta from that. So I know r is going to be equal to the square root of 1 squared plus 1 squared. So it's going to be equal to root 2. My theta is going to equal tan minus 1 of 1, which in this case is pi over 4. Then stick it all into the polar form and see what we get. So for this one, z is equal to root 2 bracket cos of pi over 4 plus I sine pi by 4. We then raise it to the power, so it's to the power of 6. So z to the 6 is going to equal root 2 to the power of 6 times cos of 6 pi over 4 plus I sine 6 pi over 4. So simplify all the parts of this and let's see what we get. So root 2 to the power of 6, that's going to equal 8. Cos of 6 pi over 4, well, 6 pi by 4 is out with our negative pi to pi range. So we take away 2 pi to bring it back. So 6 pi over 4, take away 2 pi, that's the equivalent of 6 pi over 4, take away 8 pi over 4, that's going to then equal negative 2 pi over 4, which is going to equal negative pi over 2. So what we've then got is we need to substitute that in. And if we substitute it in, using the rules when we've got negatives, what we end up getting is cos of pi over 2, take away I sine pi over 2. So now that we've got that, we can simplify it and see what we get. So cos of pi by 2, cos of 90 is 0, sine of pi by 2 is 1. So for that, I end up getting negative 8i. So I've got the first part, I've got my numerator. Now I need to get the denominator, I need to get the bottom. So I've got 1 take away I times the square root of 3 to the power of 4. So same initial steps, find it in polar form, then we take it from there. So I need my r, well in this case I know r is going to equal square root of 1 squared plus negative root 3 squared. So 1 squared is 1, negative root 3 squared is 3, 1 plus 3 is 4, square root of 4, again, hope you know that by now, is 2. Theta is equal to tan minus 1. Remember, it's y over x, so imaginary part over real part of negative root 3. Tan minus 1 of negative root 3 in this case quite simply gives me negative pi by 3. So if I'm substituting these into the parts, what I end up getting for z is I get z equals 2 bracket cos of negative pi over 3 plus I sine of negative pi by 3. Now remember, keep the negatives there with the angles. We may have to do some work onto it later on after we raise it to the power. So we're going to raise it to the power of 4. So it's z to the 4 is equal to 2 to the power of 4 bracket cos of negative 4 pi over 3 plus I sine negative 4 pi over 3. So 2 to the power of 4, that gives me 16. Negative 4 pi over 3, what again I have to do is this time add on 2 pi to bring it back into my range. So if I do negative 4 pi over 3, add on 2 pi, what I end up getting is I'll have 16 bracket cos of 2 pi over 3 plus I sine 2 pi by 3. And if I calculate each of those and multiply at the bracket, what I'll end up getting is 16 bracket negative a half plus root 3 over 2 I I can multiply out the bracket for that, and I get negative 8 plus 8 root 3 I. So I've got that for the denominator, I've got this for my numerator. If I then stick it together, what I end up getting is negative 8I over negative 8 plus 8 root 3 I. What I could have done if I fancied it was take 8 out as a common factor on the bottom and the numerator to cancel it all out. What I then end up getting is I get negative I over bracket negative 1 plus root 3 I on the denominator there. And then what I want to do at this stage is get rid of the imaginary number on the denominator, so I multiply the top and the bottom by the complex conjugate of what's on the denominator to eliminate that out. So what I'm going to do in this case, I'm going to multiply the top and the bottom by negative 1, take away root 3i. Now remember, on the bottom it's negative 1 plus root 3i, so to get rid of it, revert the sign in the middle, and that's why it's negative 1 minus root 3i. So if I look at the top to begin with and multiply all of that out, I'll get negative I times negative 1, so I'll end up with I. I'll then end up with negative I times negative root 3i, so I'll get root 3i squared, but I squared is negative 1, so that will then end up giving me just negative root 3 again. So the top, I'd end up writing it as negative root 3 plus I. My denominator, what I'd end up using essentially is the same format as difference of two squares. So for that, I'd end up doing negative 1 squared, take away the second part of this squared, the root 3i squared. So negative 1 squared is 1, take away root 3i squared, so root 3 squared is going to give me 3, I squared is going to give me negative 1, so it's take away negative 3, so it's going to be plus 3, so I'm going to get 4. So if I stick that all together, what I end up getting is I get negative root 3 plus I over 4, which I can simplify to negative root 3 over 4 plus a quarter I. So there you go, that's it simplified into the final form that we are after. Remember, one like this where you've got powers on the top and the bottom, don't just jump straight to the complex conjugate. I know it's natural, that's what we initially look at because we want to get rid of the imaginary part, but we have to have just the bracket with no power involved. Get rid of the power, use the Moivres theorem to do that, then get rid of the imaginary part on the bottom, follow those steps, and you'll be laughing when it comes to one like this.